Hello, I'm Wei Long from Imperial College, and today I would like to talk about my work on thermal electrochemo-mechanical modeling of lithium-ion batteries. This is the outline of this talk. Except introduction and summary, there are three main sections about electrochemo-mechanical coupled battery model, its implementation in Python, and applications to battery packs. Introduction. The question to ask is why mechanical effects are important for lithium-ion batteries. The figure below shows the main battery degradation mechanisms from our recent paper. I highlighted those from mechanical effects, including particle fracture and ion formation. Details of other degradation mechanisms are referred to the paper below. From this plot, we can see that mechanical effects are very important to understand battery capacity degradation. There are many studies in literature. One is on the particle size dependence of particle fracture. It has been found a critical diameter about 150 nanometers for silicon particles, below which there would be no fracture. At the cell level, it has been found localized particle fragmentation close to the separator, with about 35% penetration of electrodes. However, it's unclear how to link particle-level behaviors to cell-level performance. So the research questions in this talk are how to model the mechanical behaviors of lithium-ion battery cells, how to understand the localized particle fragmentation, how to use the model to optimize battery pack design. To answer those questions, let's start from the electrochemo-mechanical coupled battery model. The model is a physics-based model, which is also known as the DFM model. Instead of modeling battery cell in 3D, we use simplified 1D model for cathode, separator, and anode. Each electrode particle is described by an ideal theory. There are many mechanical models developed for single electrode particles. They are based on the equilibrium of stress and define the relationship between strain and the lithium concentration. We can get the analytic solution of those equations for stress and displacement as a function of particle radius and the lithium concentration. From this solution, we know that there are two states in electrode particles. For lithiation, the outer layer is under compression, while the inner layer is under tension. The delithiation is the reverse of lithiation. There is also a study on the critical particle size and discharge rates on particle fracture. For particles with larger sizes and under high C rates, they are more likely to have particle fracture. Our work is to link those particle-level studies to battery cell-level performance. The battery model is based on the DFM model, and we introduce the strain energy to the chemical potential and modify the conservation of species flux equation. The thermal model is based on the heat balance, where the cell average temperature is controlled by the reaction heat minus the convective heat and the radiation heat. The electrode material properties show thermal dependence, where the Arrhenius law is applied. The thickness change of the cell is controlled by thermal expansion and the deformation by intercalation from the mechanical model. Then we use the model to analyze commercial battery cells. We take the Anatech cells for instance. The parameters are listed in this table, and on the right-hand side are the curves of volume change, open circuit voltage, and entropy for both electrode materials. We use the model to calculate the response of voltage, temperature rise, and thickness change. The results show very good agreement with the experiments. Those results also show that deformation by intercalation is 10 times larger than by thermal expansion, which shows the importance of mechanical models. We calculated the results at different time steps marked from A to H, and the results are on the right-hand side. From this plot, we can see that the electrode particles close to the separator have more lithium concentration gradients. Those gradients lead to high stress close to the separator. This result can be used to explain the localized electrode fragmentation in experiments. When the current is increasing, there are more stress generated close to the separator, which lead to particle fragmentation. There are also quantitative results of particle cracking in literature. For NMC particles, there is about 33% of particles being cracked. In comparison, the amount is only 10% at the current collapse site. Implementation in PyBEM. We have written the mechanical model to PyBEM, and it's very easy to use. There are 3 steps to use the model. At first, we define the experiment of working conditions, and then we choose the right options to get the battery models. The mechanical model is under the option of particle cracking, where you can define it for both electrodes or either electrode. Thirdly, we run the simulation. At the bottom are the results of terminal voltage, average stress, and particle crack propagation. There are also other outputs of lithium concentration and potential distributions in both electrode and electrolyte. More details can be found in the website of PyBEM, and you can run the notebooks to get those results. Applications to battery packs. One work we have made is on the uneven currents in battery packs. We studied the cell-to-cell variations, which can cause significantly uneven current distributions among battery cells. The placement of bad cells can lead to 10% difference in power at high series. When cells are assembled to a pack, they get lower performance compared with single cell in average. We also studied the thermal gradients among those cells in a pack, and the results show that thermal gradient can significantly affect lifetime of a battery pack. This result can guide battery pack cooling strategy for a better thermal management. Another application is battery pack design tool. We link PyBEM function to Simulink, so it can be easily used by industry. The configuration of a battery pack is designed by Simulink, and the battery cells are modeled by PyBEM function. In this way, we can make use of the advantages of both PyBEM and Simulink. This work is under collaboration with Thomas Tranter from the UCL group. Summary: we have introduced the coupled mechanical model for lithium-ion batteries. This model can be used to predict stress and volume change and to explain electrode fragmentation. Then we implemented this model to PyBEM, and it's very easy to use. It's compatible with different battery models of PTD and single particle model, and we are working on the coupling with SEI and lithium plating for battery capacity degradation. Then we introduced the applications to battery packs. We studied the cell-to-cell variations and temperature gradients, and developed a battery pack design tool by combining PyBEM and Simulink. That's all. If you have any questions, you can submit them to those platforms. We will answer them online. Thank you.